An explanation for atomic spectra came early in the 20th century from a famous physicist who created a new model of the atom. He brilliantly synthesized the work of other scientists and brought a fresh perspective to physics that began the transition to the quantum model of the atom. His name was Niels Bohr.
Rutherford's model of the atom left some questions unanswered. According to the rules of electromagnetism, an orbiting electron should continually radiate energy outward and eventually spiral into the nucleus. The spectroscopic evidence shows that light is emitted only in very specific frequencies. Bohr began his investigation of the structure of the atom by patching together different ideas that came out of earlier scientific work on the atomic spectra of hydrogen and the relationship between energy and frequency of light.
The atomic spectrum provided a window into the atom, but it revealed a colorful code scientists could not decipher for many years. In the late 19th century, many scientists tried to find regularities in emission spectra. Johann Jacob Balmer, a Swiss schoolteacher, focused on the spectrum of hydrogen gas because it is the simplest element. In 1885, Balmer discovered a pattern in the lines of hydrogen. He developed a formula that explained the different frequencies according to a simple mathematical relationship. Balmer's equations showed the mathematical regularity of the lines in the hydrogen spectrum. However, he could not account for it.
In 1900, a German physicist named Max Planck suggested that the energy of light is directly proportional to its frequency. Planck developed the formula E equals h nu to show this relationship between the frequency and energy of light. In this equation, E is energy measured in joules and nu is frequency in hertz. H is a proportionality constant known as Planck's constant. The value of Planck's constant is 6.63 times 10 to the negative 34 joules seconds. What happens to the energy when the frequency changes? When the frequency increases, the energy increases, and vice versa.
Niels Bohr realized that Planck's formula held clues to explain the relationship between the lines of the hydrogen spectrum that Balmer observed. Bohr synthesized these two seemingly unrelated pieces of information and took a brilliant leap into uncharted waters.
Remember, Rutherford had proposed a planetary model of the atom in which electrons orbit the nucleus. Bohr kept the idea of orbits, but added some restrictions. Bohr proposed that the orbits of electrons exist only at specific distances from the nucleus. In-between orbits were not allowed. In other words, the electron could be here, or here, or here, but never in between. Imagine placing a rock on different steps. The rock will sit comfortably on this step or this step, but you cannot place a rock between steps and expect it to stay there. Just like the distance of the rock from the floor, the distance of an electron from the nucleus can only have specific discrete values. Electrons at these different levels possess different amounts of energy. Electrons in orbit around an atom can possess only discrete amounts of energy, not a continuous range of energies. Generally, the farther away the electron is from the nucleus, the higher its energy level. The levels are numbered starting with 1 at the lowest energy level.
Bohr claimed that the orbits suggested by Rutherford corresponded to certain fixed amounts of energy, with no orbits in between. Because electrons were in these stable orbits, they did not spiral downward toward the nucleus. Bohr proposed that electrons can jump between levels. When an atom absorbs energy from heat or light, an electron can jump up to a higher energy level. However, an electron eventually loses the energy it gained and falls back down to a lower energy level.
To explain the atomic spectrum of hydrogen, Bohr hypothesized that when the electron falls from a higher to a lower energy level, it gives off energy as light. The amount of energy that the electron possesses at different levels is discrete, so the amount of energy lost when the electron falls to a lower level is also discrete. Since frequency is related to energy, only specific frequencies of light are emitted when the excited electron falls from a higher energy level to a lower one. The frequency is determined by the energy difference between the different levels.
When the rock is placed on a higher step, it has more potential energy. When it rests on a lower step, it has less potential energy. The amount of potential energy lost depends on how far it falls. Notice the steps are different distances apart. If the rock falls from level 4 to level 3, the loss of potential energy is less than if it falls from level 2 to level 1. In the same way, the frequency of light emitted by an excited atom as an electron falls to a lower energy level depends on the difference between the energy levels.
Let's look at the hydrogen spectrum again. Select a line to see the energy level change that causes it.
Bohr's model of the atom was very bold and broke sharply with the planetary model in which electrons obey the laws of classical physics. Proposing that electrons jump from one energy level to another was like suggesting that Mars could jump instantly down into Earth's orbit.
No one knew why the Bohr model worked, but everyone agreed that it did. Bohr's model predicted the diameter of the atom, and explained a great deal about chemistry. It provided a satisfactory explanation for the existence of line spectra, but it only worked well for hydrogen. Attempts to extend it to other elements had limited success.
The idea that electrons move around the nucleus in definable pathways was eventually abandoned in favor of an emerging theory, quantum mechanics. In fact, scientists now think the exact location and path of an electron cannot be pinpointed.